In this section, we're going to revisit limits. But this time, we're going to allow the input to either go to infinity or observe what happens when the output goes to infinity. But the mathematics needed to do this properly, we have to review or revisit the idea of infinitesimals and infinite numbers that we explored quite extensively back in chapter 1. So let me remind ourselves our rules for arithmetic with infinitesimals, finite, and infinite numbers. This is right out of the book, chapter 1. If we let epsilon delta be infinitesimals, b and c hyperreal numbers that are finite but not infinitesimal, and h and k are infinite hyperreal numbers, then kind of working through, we know that if epsilon is an infinitesimal, then its reciprocal is infinite. We know that if b is finite, its reciprocal is finite but not infinitesimal. And if h is infinite, then its reciprocal is infinitesimal. Adding infinitesimals, we stay infinitesimal. Finite with infinitesimal is finite. Finite's added together, finite. Infinite plus an infinitesimal or infinite plus a finite are infinite. These are key things. What we'll run into the most, however, are products and quotients. So if I multiply two infinitesimals, or even if I multiply a finite infinitesimal, I get an infinitesimal. If I multiply two finite numbers, it will be finite but not infinitesimal. And if an infinite number is multiplied by a finite number, or two infinite numbers are multiplied together, it will be infinite. On the other hand, quotients, anytime you've got an infinitesimal divided by a finite or infinite number, or if I divide by an infinitesimal, it'll be infinitesimal. Ratio of two finite numbers are still finite. But now if I divide by an infinitesimal, I'll get infinite, provided that the denominator is not 0, and roots and so forth, and other functions. Where we're going to have to do some algebra, if you recall, is when we have indeterminate forms. If I've got the quotient of two infinitesimals, the quotient of two infinite numbers, the product of an infinite and an infinitesimal, or the sum of two infinite numbers. And so looking at these cases in chapter 1, why are they indeterminate form? Well, in all these cases, I've got infinitesimals, right? If the, in this case, you could do the division and this would just be infinitesimal. Here you could do the division and this would be infinitesimal. Product infinitesimal, the difference infinitesimal. On the other hand, if we have situations like this, we've got finite numbers, and in this case they're all equal to 1, and similar algebra tells us that these guys would be infinite numbers. So if I've got an indeterminate form, right, which is anything that looks like an infinitesimal divided by an infinitesimal, an infinite divided by an infinite, the product of an infinite and infinitesimal, or the sum of two infinite numbers, I'm in an indeterminate form, and we have to do some kind of algebra to determine, is it infinitesimal, is it finite, or is it infinite? Okay, so let's introduce here now the new types of limits we're going to investigate. So the first two can be thought of as limits at infinity, and the second two could be limits that approach infinity or go to infinity. And what we mean in the first case, that so we've got the input in these both cases going to infinity or negative infinity. And if we say the limit exists, it means that f of x is infinitely close to L. So same idea of a limit, that the output is infinitely close to L whenever x, in this case because it's a positive infinite, whenever the input is a positive infinite number. Right? In both these cases, x will be in the set of infinite numbers. Remember, I used this double script m to note infinite numbers or massive numbers. On the other hand, if we are saying that a limit goes to infinity, now let me be very clear what's being said here. These limits do not exist because this is not a real number and this is not a real number. So we're not saying that this limit exists, but we are saying that it fails to exist in a very particular way. What we're saying is that x gets close to c. Now, c is a real number. Then the output gets infinitely large. In other words, f of x is an infinite number whenever x is close to c. So in this case, we're saying that not x itself is an infinite number, but f of x, the output, will be in the set of infinite hyperreals. So that's the key distinction. This one, the input is an infinite number. In this case, the output is an infinite number. And let me post up an image that kind of gets this idea across. And what we're saying in the first case, right? So as the input x goes to infinity, so it's as we march out into the infinite numbers. So x is an infinite number. As x approaches infinity, the output will get close to this real number L. Right? And so if we brought out our infinite telescope, we could zoom way out to here at infinity, and we'd see that if I put an infinite number, say h, into the function, right? So x is h, the output is f of h, then I couldn't tell the difference between the dotted line and the curve of my function until I brought out an infinite microscope, and I'd see, oh, this point is infinitely close, right? F of h is infinitely close to L. Right? So that's the first case in which we have the input x going to infinity and the output f getting closer and closer to this real value L. Now, in the second case, the image would look something like this. And here we have that the input is approaching c, right? It's getting infinitely close to c. But the output, this curve f of x, is, in this case, going to negative infinity. It's shooting down. And again, I could take in my infinite telescope, look out at infinity. Looking out at infinity, I would see that, right, if I'm infinitely close to c, then I must be just an infinitesimal difference from c. And again, it look like a vertical up and down line. However, if I brought in the infinite telescope, or infinite microscope, sorry, I would see that I'm getting closer and closer, but it's just shooting down. And so in this case, as x gets infinitely close to c, f of x gets infinitely close to negative infinity. In other words, that f of x will be, if x is infinitely close to c, then f of x would be a member, in this case, of the negative infinite numbers. Okay, so that just kind of gives some, hopefully, picture of what's going on, some sense of what we're doing with the notation here. But of course, what we really need to do is work some examples. So let's look at this first case. Let's say we want to investigate the limit as x goes to 0 of 1 over x squared. So this is our function, 1 over x squared, and we're going to let x get infinitely close to 0. So how do we work this out? Well, over here on the side, we'll do some work. We'll say, let's let x be infinitely close to 0. Well, if x is infinitely close to 0, this means that x is an infinitesimal, right? So if x is an infinitesimal, And now I'm going to put it into our function. Then 1 over x squared. Well, let's go back to our rules, and we know that if I divide or take the reciprocal, really, of an infinitesimal, right? So 1 divided by an infinitesimal is infinite. So since x is an infinitesimal, I should have mentioned this, since x is an infinitesimal, x squared is also an infinitesimal. And by the rules of reciprocals, then this is an positive, everything's positive, right? This is a positive infinitesimal. And so this is in the set of positive infinite numbers. And since that's an infinite number, we could say that this then is equal to infinity. And again, we're abusing the sense of infinite because this is not a real number. Right? It's not a real number. So this limit, and I can't stress this enough because I know there's confusion in the language, that this limit does not exist. Because when we talk about limits existing, we're saying they go to a real number. But infinity, this symbol, is not a real number. All this is saying is that really what it's saying is that if x is infinitely close to 0, in other words, if x is an infinitesimal, then 1 over x squared is in the set of infinite numbers. And so by just notation-wise, we just simply say the limit as x approaches 0, 1 over x squared is infinity, even though we know it doesn't exist. It's just a very special case of not existing. So let's look at another example. Right, so let's say we want to know what's the behavior of the limit as x approaches 0. In this case, we're going to do it from the right-hand side of 1 over x cubed. What is it equal to? Again, we'll do a little bit of work. If we want x to be infinitely close to 0, so x is infinitely close to 0, but since it's on the right-hand side, it's bigger than 0. And this means that x is a positive infinitesimal. But if that's a positive infinitesimal, then so is x cubed. Right? That's what's in the denominator. So that's really the expression of x we want to investigate, but that this tells us that 1 over x cubed, by the reciprocal rule, is a positive infinite number. And so since 1 over x cubed, if x is infinitely close to 0, 1 over x cubed is a positive infinite number, we would say that this is positive infinity. On the other hand, if we wanted to look at the limit as x approaches 0 from the left of 1 over x cubed, so now we're saying that x is infinitely close to 0 and x is less than 0, which tells us that x is a negative infinitesimal, which then tells us that x cubed itself, right? Because if I take a negative number and cube it, it's still negative. So this is a negative infinitesimal, which then tells me that 1 over x cubed is a negative infinite number. And from that information, that little work over there tells me that this limit is equal to negative infinity. Let me kind of draw the graph of 1 over x cubed at 0. So looking at the function, what it says is that as I approach x from the right, so as x is approaching 0 from the right, the output is going to be going to negative or positive infinity. So the output has to go something like this. However, if I approach x from the left, so if I approach x or 0, sorry, from the left, then the output has to be going to negative infinity, and the graph will look something like this. And this is the behavior, and we'll use this in the next in section 5.3 to help us graph the behavior of functions. And what we've got going on here is an asymptote. Right? This is an asymptote. And you should have studied asymptotes back in algebra, so these aren't anything that new, but now we've got the language of limits to help us define when asymptotes occur. But again, we'll explore that further in section 5.3. So now so in both these cases, I was looking at the first example, the second example, in which I've got the input going to some real number and the output went to either positive or negative infinity. Let's do an example where the input itself is going to infinity. So we'll look at the limit as x goes to positive infinity of the function 5x plus 6 divided by x squared minus 4. So now, unlike the other ones where in these two examples, I let x be infinitely close to 0 in all three of these because that's where the limit of the input was going to. In this case, I want the limit as x goes to infinity. So my assumption is that, and it's positive infinity, so my assumption is that x is in the set of positive infinite numbers. Right? So I'm going to look at this function when x is a positive infinite number. And so now what I'm going to do is I'm hoping, if possible, that this limit exists and will be a real number, which means I need to let x be infinite and compute what the standard part is. And this should be very familiar to you back from in chapter 1.4 or 5 when we were determining whether this, what kind of number this was. Because notice, if x is infinite, then the top is infinite, right? Because finite times infinite is infinite, infinite plus finite is infinite. And down here, infinite squared is infinite, subtract a real number. The bottom is an infinite number. Right? So what we have going on here is exactly the indeterminate case where we have infinity, an infinite number divided by an infinite number. And we have to determine, is it infinitesimal? If so, the limit would be 0. Is it finite? Then let's determine what that finite number is. Or is it also infinite? So we're going to use the algebra strategies that we developed back in chapter 1. And so if x is an infinite number, we know the top and bottom is indeterminate form. So then 5x plus 6 over x squared minus 4. And if you recall, to determine this indeterminate form, what it is, when we had infinite over infinite, we factored out the largest power of x. In this case, it's x squared. That was our standard method for determining. So let's factor out an x squared. Up here, we get x squared times 5 divided by x plus 6 divided by x squared. And on the denominator, we get x squared times 1 minus 4x squared. and the x squareds will cancel out. So these guys cancel. That was the whole reason we pulled out, well, one of two reasons. One is that they would cancel. The second reason, if you recall, this is now an infinitesimal, so it's infinitely close to 0. This is an infinitesimal, so it's infinitely close to 0. This is finite, and this is an infinitesimal. And so the top is infinitesimal, the bottom is finite. So we now know with quite certainty that the standard part of 5x plus 6 over x squared minus 4 is equal to, well, the top is infinitesimal, it's infinitely close to 0, so the top is 0. And the bottom is infinitesimally close to 1, so it's divided by 1, which we know to be 0. So when x is an infinite positive number, then the standard part of this ratio is 0, and now we can say this limit is equal to 0. So the limit as x approaches infinity of 5x plus 6 divided by x squared minus 4 is 0. In the subsequent videos, we'll just work out a bunch of examples in hopes to just develop or remind you really how we work with infinitesimal and infinite numbers in order to determine, in this case, what the limit, but it all goes back to the same methods that we used to determine when we had indeterminate forms what kind of value you had. It's all going to come back to using the algebra we developed and determining what kind of value we had when we were looking at an indeterminate form. So at this point, I'd encourage you to go back to your notes and refresh all the things that we worked out, because it's going to come into play in all the calculations and algebra throughout this section.